A careful examination of the objects in our solar system provides convincing evidence that the Earth and other planets are unique worlds with unique characteristics. In this lecture, I want to take you on a tour of the solar system. We'll start nearest the Sun at the swift, tiny planet Mercury, and we're going to work our way outward to the cold, dark, distant worlds of Uranus and Neptune. Now, I absolutely love this subject. Each planet is different. It has its own personality, its own idiosyncrasies. Each planet holds surprises. Each planet is begging for more research and for new discoveries. Now, there's always a danger, of course, in trying to review 9 planets with their dozens of moons. It's easy for such a travelogue to seem absolutely overwhelming. It's sort of like visiting 13 different European cities in 14 days, and after a while it's really hard to remember which cathedral goes with which town. So I'm going to ask you to remember just a couple of distinctive words or phrases about each world, and I want to emphasize the similarities among planets as much as possible. So let's go. Oh yes, I've been remiss in not telling you about another teaching company course. It's Understanding the Universe, an Introduction to Astronomy by Alex Filipenko. That's a good place to get even more information about these fascinating subjects. Okay, as we embark on this tour, keep in mind how the solar system formed. That was about 4.5 billion years ago from a nebula of dust and gas. Now, according to Laplace's nebular hypothesis, the solar system began as a large, irregular cloud of dust and gas, and that material was in large part the remains of previous supernovas. The amount of heavier elements like iron and magnesium suggests that the atoms that make up the solar system went through perhaps a half a dozen previous cycles of exploding stars. Now eventually, that dust cloud became more compact. Gravitational collapse was perhaps triggered by the shock wave of a supernova, which caused local density increases. And so the cloud shrinks down, it concentrates the mass. The central mass then becomes the Sun. That holds 99.9% of the mass of the solar system. Then smaller accumulations of mass became planets. The planets in orbit, they carry most of the angular momentum of the solar system. So when the Sun got large enough to trigger nuclear fusion reactions, it began to send out a solar wind past the planets. And the hotter regions close to the Sun were stripped of most of the hydrogen and other gases. That left behind 4 rocky terrestrial planets. And then farther out, gases could condense to form the 4 gas giants, or the Jovian planets. So that's kind of a capsule summary of planet formation. In this lecture, I'm going to examine the planets of the solar system in a lot more detail. I have to begin with a key point. We live in a golden age of planetary exploration. Planetary probes by NASA and other agencies in Europe and Asia have now visited every planet except for Pluto. We have, in the past quarter century, obtained astonishing close-up photographs of alien worlds, of new moons, many unexpected features of these celestial neighbors. Our spacecraft have actually landed on Mars and Venus. They've penetrated Jupiter's dense atmosphere. We've even visited and landed on an asteroid, and we have exciting plans to return samples from a comet. Never before in history has the pace of planetary discovery been so rapid. We've learned more about the planets in the last quarter century than in the previous 400 years since the time of Galileo. And because of NASA's public outreach and educational policies, every one of us can share in this exploration as it's happening, live on TV and on the internet. All you need to share in this great human adventure is a little background information, and then all you need to remember is www.nasa.gov. Well, let's start with the innermost planet, Mercury. When you hear the planet Mercury mentioned, I want you to remember 2 words, blasted and dead. Mercury is the planet closest to the Sun. It's a desolate world. It's a forbidding world. Its small size and its proximity to the Sun have made Mercury extremely difficult to observe with Earth-based telescopes. It's hard to get a clear view of a relatively dim object when there's so much glare from the bright Sun. Now, Mercury's orbit is quite elliptical. It gets as close as 43 million kilometers to the Sun and as far away as 70 million kilometers. And look at this, Mercury's orbital period is short. It's just 88 Earth days, while a day on Mercury lasts 176 Earth days. So the Mercury day turns out to be gravitationally locked, as you see here, and it's locked in at exactly twice as long as the year. Our knowledge of the planet was greatly enhanced by Mariner 10. That's the only spacecraft so far to fly by Mercury. But there's another NASA mission on the books, that's Project Messenger, scheduled to be launched in 2004. The plan is to place a spacecraft in a polar orbit around Mercury. That's to provide a complete coverage of the surface. Now, such a mission is exceptionally complicated. That's because the orbital dynamics, the sun's gravity is so strong that it's hard to achieve a stable orbit around Mercury without having the craft fall into the sun. And this mission also requires that almost all the weight that the rocket lifts is fuel. 99 pounds of fuel is required for every 1 pound of payload. And in addition, the entire spacecraft has to be shielded from that brutal solar radiation. So this could be by far the most challenging unmanned mission NASA has ever attempted. Well, the Mariner 10 photographs revealed a heavily cratered surface, alternately baked to 500 degrees centigrade by the sun and then frozen to minus 200 degrees centigrade on the dark side. Mercury has no atmosphere, and so it has no erosion to wear down its pockmarked surfaces. The poles on Mercury are really interesting places because the planet's tilt is exactly 0 degrees. As a result, the poles are in eternal twilight with a temperature near the boiling point of water. And it's even possible that there are small reservoirs of liquid water right near the polar surface. So perhaps I'm wrong. Maybe Mercury isn't entirely dead. But still, when you think of Mercury, remember blasted and dead. Next is Venus. Venus is our nearest planetary neighbor, both in distance and in size. So when you think of Venus, try to remember Earth-like and greenhouse effect. The orbit of Venus is nearly circular, with an average distance of 108 million kilometers from the Sun. The orbital period is 225 Earth days. That's about 2/3 of Earth's year. Now, Venus has a slow retrograde rotation about its axis. That gives a leisurely day of 243 Earth days. So this is something of an anomaly. On Venus, the sun rises in the west and it sets in the east once every 243 days. So like Mercury, the Venusian day is longer than its year. Some astronomers suggest that the unusual retrograde motion is the result of a very large impact that occurred near the end of the planet's accretion. One of the most distinctive aspects of Venus then is its thick atmosphere. It's enshrouded in an atmosphere composed primarily of clouds of carbon dioxide and of nitrogen. And to get a sense of this, the surface pressure on Venus is about 95 times that of Earth. That's a pressure of 1,400 pounds per square inch. The daytime surface temperature reaches almost 500 degrees centigrade. That's a result of an exaggerated greenhouse effect. Now, the greenhouse effect is a phenomenon that occurs when sunlight enters the atmosphere and then the sunlight's converted to heat. So greenhouse gases like carbon dioxide trap that heat and the atmosphere warms up. This may sound a little strange, but the effect is familiar if you've ever used a greenhouse to grow plants during the cold winter. Though the surface is always hidden from view, that Venusian landscape has been mapped in great detail by radar from the Pioneer Venus spacecraft. The radar maps show a planet with mountain ranges, there are cratered plains, there are volcanoes. That's evidence of a once active planet, though it's not so rugged and dynamic as the Earth is at present. And the Soviet Union actually succeeded in sending 4 Venus landers called Venera 9, 10, 13, and 14. And these spacecraft returned remarkable surface photographs of a rocky landscape. So remember, Venus might have been a lot like Earth if it hadn't been for that intense greenhouse effect. Now next is the red planet Mars. It's by far the most intensively studied of our solar system neighbors because of that strong possibility that it once had abundant surface water. By all theories, life is absolutely dependent on water. So if any nearby planet has harbored life, then Mars is the odds-on favorite. So you might call me an optimist, but when you think of Mars, I want you to cross your fingers and click your heels together 3 times and think of water and life. Mars is about half the diameter of Earth. It's just 11% of its mass. It has an elliptical orbit that averages about 1.5 times the Earth-Sun distance. As a result, Mars can be as close to Earth as 60 million kilometers and as far away as 400 million kilometers. A year on Mars is 686 Earth days. That's almost 2 Earth years. A day on Mars is coincidentally close to 24 hours. Now that is pure coincidence, but it could represent a distinct advantage to future colonists on Mars. Mars is also tilted at about 20 degrees on its axis, so it has seasons just like Earth. Mars has 2 very small irregular moons. They're just tens of kilometers across. These moons are called Phobos and Deimos. they look a lot like they're captured asteroids. Now, unlike Mercury and Venus, Mars has surface markings that are clearly visible from Earth. Remember, Mercury is too close to the Sun, Venus has too thick an atmosphere. The most prominent Martian surface features are polar ice caps, and these wax and they wane with that 686-day Martian year. The planet also shows brighter and darker reddish areas with what appeared to some 19th century astronomers as linear features. The most famous, or perhaps the most infamous of these mappers of Mars, was the American astronomer Percival Lowell, who lived from 1855 to 1916. Lowell constructed a 24-inch telescope at his own observatory near Flagstaff, Arizona, and with this telescope he claimed to see amazing lines and other surface markings. He interpreted these lines on Mars as artificial canals for the irrigation of a dying planet. And he published detailed maps of more than 500 different canals, and he said that the extensive network points to an efficient government. Well, it was quite an extrapolation from sketchy observations. The Mariner spacecraft missions, those were in the 1960s. They returned the first close-up pictures of the spectacular Martian surface. And what Mariner cameras found was amazing. They're natural water-carved valleys, they're cratered plains, they're huge volcanoes, the largest volcanoes anywhere in the solar system. These are seen. Even higher resolution pictures are being provided by NASA's Mars Global Surveyor, which has revealed all kinds of systems of what appeared to be braided streams and water-worn valleys. These observations suggest that Mars once had lots of water, perhaps even a large ocean, and perhaps a thicker atmosphere as well. So think how Mars must have changed over the past 4.5 billion years. Volcanoes clearly brought water to the surface early in the planet's history. So where did all that water go? Turns out at less than half of Earth's gravity, water molecules, they can escape into space. This is a gradual, but it's an inexorable process. We've also learned a lot about Mars from landers that return data from the surface. The Viking lander missions of the 1970s returned pictures of a dry, barren, a blasted world, a desert world. The pressure of the carbon dioxide atmospheres was found to be only 0.5% of Earth's atmosphere. Even so, there are intense dust storms with winds over 100 kilometers per hour that scour the surface over and over again. And then there was Mars Pathfinder mission, NASA's mission, which touched down on July 4th, 1997. That featured both a lander and a 6-wheeled, 23-pound rover named Sojourner. The Pathfinder mission was a glorious achievement. It returned spectacular three-dimensional pictures of the rocky surface. The mission also provided unparalleled data on the chemical analyses of rocks and soils, and those actually turned out to be very similar to the analyses on Earth. By the way, the famous red color is a consequence of iron oxides, so basically Mars is colored by rust. And as I mentioned in the last lecture, NASA is already planning Mars sample return flights for sometime in the 2010s, and my laboratory is just itching to get a hold of some of those samples. We want to study the composition of Mars rocks and minerals, and we're also going to look carefully for any possible signs of life, whether it's recent or fossil life. And to me, the most exciting opportunity in space is actually a human mission to Mars. Of course, there are lots of hurdles, and such a trip would be risky, but I'd sign up in an instant for a chance to stand on another planet. Think about that. Okay, on beyond Mars, we come to the asteroid belt. That's a broad band of rocky debris. It's about halfway between Mars and Jupiter. In fact, it's just about where you might expect to find another terrestrial planet. There are perhaps 50,000 objects that are kilometer in diameter or larger in that asteroid belt. So your key phrase here is big rocks. Here's a picture of the asteroid Eros. It's 21 miles long. It has its own little moon. See here? Then, according to one theory, the strong gravitational force of Jupiter prevents these objects from ever clumping together to form a planet. Now, some of the asteroids, perhaps as many as 1,000 larger than a kilometer, have highly elliptical orbits that actually pass inside Earth's orbit. The idea is that these were once a part of the asteroid belt, and these objects may have been knocked out of the asteroid belt by passing comets or by other collisions. Occasionally, an Earth-crossing asteroid actually hits the Earth. Lots of prehistoric impact sites have been found, including the spectacular Canyon Diablo meteor crater in Arizona. You can actually visit that site. Indeed, we now have strong evidence that an asteroid perhaps 20 kilometers or more in diameter hit the Earth near the modern-day Yucatan Peninsula of Mexico. That was 65 million years ago. And that epic blast, that resulted in the extinction of the dinosaurs and many other groups of animals and plants. And that's only the most publicized of the many big impacts that altered life on Earth. That's why Carl Sagan wanted to map all the Earth-crossing asteroids. And he also wanted to see the world work together to develop a means to deflect an asteroid before it hit us. The character of the solar system changes radically beyond the asteroid belt in the realm of the Jovian planets. Now, Jupiter is by far the largest of these giant planets. It's a ball of hydrogen and helium. It's about 2.5 times as massive as all the other planets combined. Whenever Jupiter comes up in conversations, think of two phrases: bad weather and amazing moons. First, think about what happens to balls of hydrogen in space. We've seen lots of these objects. If such a ball contains 10 times the mass of the sun, it'll end up as a supernova. The star will burn relatively quickly and then it'll blow up. If the hydrogen ball begins with about the mass of the sun, it'll end up as a red giant star and then a white dwarf star. So there's no explosion. It just gets cooler over time. And if the hydrogen ball has a mass a tenth of the sun, it ends up as a brown dwarf. That object just barely maintains nuclear fusion in its core, and it'll continue to burn slowly for hundreds of billions of years. And now we come to Jupiter. If an object begins with 100th or 1,000th of the sun's mass, the nuclear fusion never gets underway. These objects are the gas giant planets. So you might think of a gas giant planet like Jupiter as a failed attempt to make a star, but I think gas giant planets are wonderful objects in their own right. Now Jupiter, it's 5 times the Earth-Sun distance. It orbits the sun every 12 Earth years. But a day on Jupiter is short. It's only about 10 hours. That means the planet rotates so fast, the planet actually bulges about its middle. And this flattening is pretty obvious in pictures of the planet. So, bad weather. That's one of the two phrases you're going to remember about Jupiter. It's a direct consequence of the planet's rapid rotation. This rotation breaks Jupiter's thick atmosphere into fast-moving bands and swirls. And you can imagine this process. Gases at the equator are moving around faster than gases at higher latitudes. So shearing occurs. Huge masses of gas flow past each other, and they create immense vortices which whirl around at hundreds of kilometers per hour. The exact same thing happens on Earth, albeit on a much more gentle scale. Atmospheric shearing on the Earth causes the trade winds, for example, but on Jupiter, the effect is absolutely awesome. Think about the concept of weather on Jupiter. Compared to the Earth, Jupiter is much bigger, it's much faster, it has a much deeper atmosphere, so shear causes immense cyclonic storms. The largest of these storms is the famous Great Red Spot, and that weather pattern is so large it would swallow 100 Earths. And the storm has been raging for centuries, for as long as astronomers have had telescopes powerful enough to see it. A lot of our detailed knowledge of Jupiter has come from space probes, notably NASA's Voyager spacecraft of the 1970s, but also the more recent Galileo and the Ulysses probes. These extraordinary missions include flybys of all the gas giant planets, and they produce the most amazing photographic record, plus measurements of magnetic fields and gravity and reflectance spectra and a lot more. These missions, they return a series of absolutely spectacular photographs of Jupiter's violent surface weather. And they also accumulated volumes of data on many aspects of Jupiter and its unexpectedly dynamic moons. So let me tell you about just a few highlights of these missions. The probes documented Jupiter's intense weather in unprecedented detail. This photograph of the Great Red Spot shows storms within storms as the giant vortex produced eddies that are themselves vastly more powerful than the Earth's strongest hurricanes. It turns out that the atmosphere is more than 100 kilometers deep, and it's composed of about 79% hydrogen and 20% helium. But Jupiter's clouds are gloriously colored because of a whole diverse suite of carbon-based molecules. Now, it's very possible that intense lightning in the storms provides a source of energy for the synthesis of some of these organic molecules. That's what colors the atmosphere. Another aspect of Jupiter is its very intense magnetic field. Jupiter's field is 10 times stronger than Earth's. At present, the origin of this intense field isn't known. One theory is that the magnetic field is generated in an interior region of metallic hydrogen. Recall that hydrogen, when it's squeezed to extremely high pressure, becomes a colorless solid, which may ultimately wind up as a metal with freely moving electrons. Now, metallic hydrogen at very high pressure could be a very efficient electrical conductor. So that material, combined with rapid rotation, could set up big electrical currents. And remember, electric currents moving in a loop produce magnetic fields. Okay, astronomers have identified more than a dozen moons of Jupiter. They range in size from asteroid-like bodies less than 20 kilometers in diameter to planet-like Ganymede, which is more than 5,200 kilometers in diameter. Actually, the number of moons keeps increasing as more detailed sky surveys are done around the planet. But the 4 largest moons are really special. You know, many scientists, if asked to identify one place in the solar system they'd like to visit, would put one of Jupiter's 4 largest moons at the top of that list. That's why I want you to remember amazing moons when you think of Jupiter. These 4 largest and most interesting moons are the Galilean moons. That's Io, Europa, Ganymede, and Callisto. These 4 moons were discovered in 1609 when Galileo Galilei first turned his telescope on Jupiter. The moons are large enough that they're easy to see even with a good pair of 10x binoculars. Now, Galileo studied these moons by making detailed drawings of their movements night after night. Because Jupiter is so massive and the moon's relatively close in, they move perceptibly in their orbits from night to night. And these moons have been at the very center of fundamental discoveries about the universe. In Galileo's day, the conventional wisdom was that all celestial objects orbit the Earth. And Galileo pointed to these moons as clear evidence that some objects in space don't orbit Earth. And then later in the 17th century, Swedish astronomer Olaus Romer used the regular orbiting of these moons as a kind of clock, and he used that to measure the speed of light. And today, Jupiter's 4 big moons are seen to be among the most dynamic objects in the solar system. 2 or 3 of these moons may be the only objects other than the Earth to have oceans of water. We now know that each of these moons is a distinctive world of its own, in many respects more like a terrestrial planet than a moon. So let me tell you about Io. That's the innermost moon. It's almost as large as Mercury, with its own atmosphere and extensive volcanism. In fact, Io is the most volcanically active place in the solar system. The reason for this activity is that it's so close to Jupiter. See, Io experiences severe tidal forces that keep the interior hot. It stretches and relaxes. This provides energy to maintain continuous volcanic activity. Astronomers can explain the behavior of Io, but I have to be honest, no one expected to see these volcanoes. I mean, they're huge. They were first seen in silhouette as mammoth plumes of material fountaining out of the moon. These volcanoes are now known to be rich in sulfur, and in detail, they're quite unlike any other place in the solar system. And then there's Europa. That's the second moon of Jupiter. That's the place I'd visit. It's the smallest of the Galilean moons, but it's by far the most interesting. That's because the surface of Europa is covered by what appears to be cracked and shifting dynamic ice sheets that may cover a thick water ocean, maybe 100-kilometer thick ocean. This discovery was really unexpected. Once again, the behavior of Europa is controlled in large part by tidal stresses. It appears that tidal stresses keep this ocean warm, so Europa may harbor the most Earth-like environment anywhere in the solar system. There could be significant circulation in the ocean. There could be hydrothermal vents with mineral-rich waters. Now, we'll know a great deal more about this moon in another few years. NASA plans a Europa orbiter mission for early in the 21st century. And of special importance will be altimeter studies that measure the surface height. See, if there's a subsurface ocean, then the moon's going to bulge much more as a result of tidal forces, at least compared to a solid moon. So NASA hopes eventually to follow up with the Europa lander and even a possible ocean probe thereafter. We're going to need to develop an ocean probe because Europa's ocean is an extremely interesting place to look for life. Water, energy, minerals, those may be the universal ingredients for life. It's intriguing that NASA is now supporting ocean floor research on Earth, in part to develop new remote sensing instruments for Europa. And then we have Ganymede and Callisto, Jupiter's 3rd and 4th big moons. They display worn, cratered surfaces that suggest long periods of geological inactivity, and yet these bodies display dynamic interior behavior that may also point to the possibility of deep oceans of water. In addition to these big 4, Voyager found several previously unknown moons. These smaller moons vary in size from a few kilometers to hundreds of kilometers. As if those weren't enough surprises, Voyager also found a series of delicate rings around Jupiter. In fact, rings turn out to be a common feature of all the gas giant planets. Well, now we come to my very favorite planet, Saturn. It has its breathtaking rings. I'll never forget the first time I saw Saturn in my backyard telescope. It's just so incredibly beautiful. Saturn is the 2nd largest planet, and your 2 words to remember for Saturn are rings and Titan. The rings are an obvious choice. You can see them with a good pair of 10x binoculars. They don't have much mass, but they extend way out, and they make Saturn a much brighter object than it otherwise would be. It has about 1/3 of the mass of Jupiter, Saturn is quite similar in composition and character to Jupiter. Like Jupiter, it's made primarily of hydrogen and helium. It has a magnetic field. It has violent weather. It has lots of moons. It's just less massive. Now, Saturn is almost 10 times farther from the Sun than Earth, and it takes almost 30 years to complete one orbit. That makes it easy to keep track of Saturn in the sky. It doesn't move much from year to year. Saturn's got a 10-hour day like Jupiter. It causes an equatorial bulge, and it causes severe weather. You get the same atmospheric shearing and intense cyclonic storms. Now, Saturn's composition, 73% hydrogen, 26% helium, with those same colorful carbon-based compounds in the violent churning atmosphere. And once again, lightning may be the culprit in forming the organic molecules. That magnificent ring is actually a complex system of ringlets that appear in detail like grooves on a record. The dynamics of this fine structure are amazing. Detailed photographs from Pioneer and Voyager 2 spacecraft revealed that the rings are made of countless tiny particles of water ice or maybe rocks coated with water ice, and they're herded into line by a series of small shepherd satellites. The ring's also very thin on edge, no more than a few tens of meters thick. Now, given the nature of Saturn's rings, it's a little difficult to know exactly what to call a moon. Astronomers have identified about 20 moons that are greater than 15 kilometers in diameter, and while most of these are regular asteroid-like bodies, the largest moon, Titan, is a uniquely fascinating world. The name Titan is thus worth remembering when someone mentions Saturn. See, Titan is actually larger than the planet Mercury, though it's only half as massive because of its composition. Titan is about half ice and half rock. You see, ice is much less dense than rock. Now, Titan has a substantial nitrogen atmosphere with a surface pressure estimated to be about 1.5 atmospheres of Earth. Voyager 1 photographed Titan and found that the surface of the moon is obscured by a fascinating orange smog that seems to be made of carbon-based compounds. The frigid Titan surface may be covered with lakes of liquid nitrogen and methane and ethane. That fact has led to a lot of speculation in science fiction novels. Someday travelers in the solar system may mine Titan for liquid fuels. And then the seventh planet, Uranus, was discovered in 1781 by the celebrated English astronomer William Herschel. He lived from 1738 to 1822. In fact, when you hear the name Uranus, think gas giant and Herschel family. Now, Herschel was born and raised in Hanover, Germany, but he went to England with his father as a teenager and remained there owing to the French occupation of his hometown. The young William was trained as a musician. He was an organist and conductor and composer in the resort town of Bath, but he loved astronomy, and as an amateur astronomer, he built his own superb telescopes. So his discovery of Uranus in 1781 won him a pension from the Hanoverian King George III. George III was king during the American Revolution, and this generous annuity allowed Herschel to devote full time to astronomy. His large telescopes allowed him to observe and catalog more than 2,500 stars, star clusters, galaxies. He studied binary stars as well, and his sister Caroline Herschel aided in these studies. She was a distinguished astronomer in her own right. She began as a singer, but like her brother, she switched full-time to astronomy when the king's pension was granted. She contributed the most detailed and comprehensive star catalogs of her day. And then his son, John Herschel, went on to become one of the great astronomers of the 19th century. Indeed, John became a scientific icon in his day, much the same as Albert Einstein and Stephen Hawking have in the 20th century. Now, the younger Herschel introduced photography to astronomy. That was in 1839. He's also the first person to have used the term negative in photography. He also made pioneering telescopic observations in the southern hemisphere as part of several naval exploring expeditions, and he cataloged thousands of binary stars and nebula. All this family history was triggered by the discovery of Uranus, which is the seventh planet. Now, Uranus is about 19 times the Earth-Sun distance. It has an orbital period of 84 years. The planet's more than 4 times the diameter of Earth and about 100 times more massive. Voyager 2 revealed that the Uranian day is about 17 hours long and that the rotation axis of Uranus is on its side relative to the other planets. So unlike other planets, each pole of Uranus receives direct sunlight for 42 years at a time. Now, like the other gas giants, it's composed mainly of light elements, hydrogen and helium. Uranus has 5 major moons, all of which appear frozen and inactive, as well as a complex system of rings. And then Neptune. The discovery of Neptune was a triumph of the Newtonian model. The existence and approximate location of the eighth planet was deduced independently by astronomers in England and in France, and that was from perturbations in the orbit of Uranus. The planet was actually discovered by French astronomers in 1846. So when you think of Neptune, think gas giant and blue. Neptune is 30 times the Earth-Sun distance. It takes light about 4 hours to travel from the Sun to Neptune, and it has an orbital period of about 165 Earth years. Most of our knowledge of the planet comes from the Voyager 2 flyby. That was in 1989. It photographed the beautiful blue planet. It has a frigid, hydrogen-rich atmosphere. It's laced with methane, 60 degrees above absolute zero. There are great dynamic weather patterns that are driven by that 16-hour rotation period. Neptune also has several moons. It has a ring complex. The largest moon, Triton, has its own methane-rich atmosphere and is a fascinating object in its own right. Well, that's quite a trip. To summarize, we visited 7 planets and quite a number of moons, as well as the asteroid belt. I've covered a lot of detailed ground, but I've asked you to remember just 2 key words or phrases for each object. So Mercury is blasted and dead. Venus, Earth-like and the greenhouse effect. Mars has water and life, we hope. Asteroid belt is a bunch of big rocks. For Jupiter, remember bad weather and amazing moons. Saturn, remember rings and Titan. For Uranus, gas giant in the Herschel planet family. And finally, Neptune, gas giant and blue. Ultimately, why should we care about the physical and chemical characteristics of these other planets? In part, our fascination arises because planets are such beautiful and complex systems, and because they've played such a rich part in the history of human knowledge. But to many scientists, the other planets hold the key to understanding our own dynamic world, and that's the subject of the next lecture.